Okay, so we are now going to start this new section, contraction and minors. It starts off like this. The author reminds us of the two fundamental containment relations between graphs. One of them is the subgraph relation and the other is the induced subgraph relation. We already know what these things mean. Now in this section we are going to meet two more such relations between a binary relation in the class of graphs. One of them is the minor relation and the other is the topological minor relation. And things are now going to start with the notion of contraction, which we have in fact already very loosely discussed in that 666 video. So let's see what Diestel has to say about contraction. Let E equal to x, y, b an edge in a graph G whose vertex set is V and edge set is E. Now by G by E, this is going to be a new graph. We denote the graph obtained from G obtained from the original graph G by contracting the edge E into a new vertex. The entire edge collapses into a vertex which we denote by V suffix E, and this new vertex becomes adjacent to the previous neighbors of the vertices x and y, which are no longer present in this new graph. So what this thing means is just what we discussed in that video also. So say this is your original graph G, where you have chosen one edge E whose ends are x and y, two vertices in G. Now besides besides only this, each of these ends may have other neighbors. X is a neighbor of y, but there may be other neighbors of y in the graph. Similarly, x may have neighbors other than y. To distinguish between these two types of neighbors, these neighbors of x and y, let's keep the neighbors of x within circles and let's keep the neighbors of y within squares. Now when we perform this contraction, we will get this graph, which now I am going to draw schematically, of course, because we cannot say, we cannot draw an actual graph if we are talking about things generally. Actual graph, of course, you will see now in a short while, because we will have an example. But just simply saying in general what this notion means, you draw schematically like that. So after the contraction, you get this graph, which we are calling G by E, G slash E. So in G slash E, we don't have the edge E. We neither have E nor its ends X and Y. In their place, we have a single vertex V, E. And the neighbors of X and Y, of course, are there. Still they are there. This new vertex VE becomes adjacent to the previous neighbors of X and Y. So that means we make VE adjacent to these previous neighbors. And you can imagine this new graph G slash E is going to be called a contraction of G by the edge E. Now this entire thing, of course, is highly non-mathematical and slightly vague. So we need to make this definition precise by writing formally precisely what the vertex set and what the edge set of this new graph are. So that's what now we are going to do. Formally, G slash E is the graph that means this is the vertex set. V prime is the vertex set of G slash E and E prime is its edge set, where the vertex set V prime is, the formal definition of V prime is this. From V, which is the vertex set of G, we have removed the vertices X and Y. And we have introduced a new vertex V, E. We can write within brackets to emphasize the fact that this VE is a new vertex. You can write where VE is the new vertex what this means is that i.e. VE is something that has come from outside of the graph G. VE was not originally, VE is an object which is not which was not present originally in the graph G at all. We have brought it from outside. Okay, so that's what we mean when we say new vertex. And now the edge set E. Edge set E prime is, it will look complicated, but we will discuss what this means. It is, first of all, it has those edges which were previously also there in the original graph and now also they are there. That is, they have remained unaffected by this contraction operation. this is the empty set, and it also has those edges which look like this, where wx belongs to the original edge set, or wy belongs to the original edge set. Oh, it's a set. Okay, so it's not difficult to understand why v prime is this. This is quite easy. This, however, looks quite what are these symbols? Let's see. Let us draw a bigger G, because now we need to look at two different types of edges in G. Oh, I could have just simply, okay, without rubbing up everything. Anyway, so this is our G, right? In G we have two types of edges. Some edges are like this, which are sitting far away from this mayhem where the contraction is going on, far away in the sense that they are totally unaffected. In what sense are they unaffected? They were there in G, here also they are present. Say if okay, let me just draw it here, it does not matter. When will you have this situation? Clearly, this will be the situation if x and y are entirely different from both v and w. In the language of graph theory, it is that situation where this edge is not adjacent to the edge E in G. In the other case, we would have something like this. And this x is suppose equal to v. If you have something like this, say this edge itself, if you had w here, then this edge is clearly being affected, because strictly speaking this edge itself is no longer there in this graph. Its place has been taken by a new edge, and that new edge is this. And why do I call this a new edge? Although w is still there, that is because the other end x is no longer present here. In place of x, we have got a new vertex v. So strictly speaking, we have got a new edge, and in fact this edge has been affected. It's been replaced with something else, this edge. This one, however, will not be replaced with anything. It will just simply sit with its ends intact. Those kinds of edges will be there clearly in this graph, and the first set consists of those kinds of edges. Why? Because the fact that x and y are both different from v and w can be expressed like this, that these two sets are disjoint. One of them has v and w and the other has x and y. Okay, so these unaffected edges will obviously be still there, but what about the affected edges? This is of course not something that is there in G. Now, which edges are getting affected? Clearly, the affected edges are here in this region of G. Now among the affected edges, we of course don't have to think anything about E. It just vanishes and it is not replaced with anything. But what about the other edges? The other edges, see, for example, you consider this edge. XW is in G. That means it belongs to this edge XW belongs to the edge set of G, but at the same time this edge is not E itself, not that edge which is being contracted. So if XW belongs to E minus E, that is XW is an originally present edge in G which is different from E, then now this will be replaced with WV. So we have a condition like that. If WX or XW, same thing, is an edge in the original graph which is not the edge being contracted, then in its place we will have WVE. Similarly, if you have say an edge YW or WY which is in G, in the original G, which is different from E, then in its place you are getting again WVE. You can see one thing that, okay, we will see that when we look at an actual example. So now we understand what E prime is. We previously also understood what E prime is, but now we understand why E prime looks like this. Okay, so that is our new edge set E prime. Now, before we look at the actual example, let us talk a little bit about the notation G/E. Why this notation? And we keep seeing this type of things in different parts of mathematics. You see this one here. You see another thing which looks like this. We are coming to it, but many people are familiar with at least this. When we see this slash, that means division in some sense, which is an operation that makes the original object smaller in some sense, or it reduces the original object into a smaller version of it. Another same type of object, but that is smaller than the original object in some sense. For example, when you divide 4 by 2, you get another integer 2 which is smaller than 4 in the usual sense of the word smaller. In its place, you can think of a group and a normal subgroup. This then is the quotient group. Why do we use the same type of notation here for groups? It is because your original group is this, which has some elements. In it you have got a normal subgroup which also has some elements in it. What the normal subgroup does, it divides the original group G into disjoint sets, non-empty disjoint sets which partition G. Now when one considers the quotient group, one can look at this thing like this. Here age is being contracted, here the set in itself is being contracted. In what sense? We in the quotient group G quotiented by n, we are no longer considering the elements in a single coset as different elements, but all of them as a single element, the coset itself, that is n. This is a single point in a single element in this group. So that means you can view just like we had the physical operation of the age being age getting diminished and eventually vanishing. You have here the physical operation of all the points coming together and merging into a single point. Just like that, the same local collapses happen inside the other cosets of n. Each one of them now becomes a single point, some nx, some ny. So the original group has got reduced in this sense. So you get quotient group. Similarly, you have quotient ring, quotient vector space, topological space. So that is why this type of notation is being used. And the thing that causes this reduction, whatever the sense may be, is written here. Here 2 is causing this reduction, here this normal subgroup is causing this reduction. In this case of graph, that a vanishing age is causing that reduction. Okay, so that's why the notation looks like this. Okay, so now we are going to look at an actual example of a contraction. Oh, I need to draw that, okay. So this is your graph G, whose edges now I am drawing. And the age that we will contract is this age, x, y. In order to further emphasize the age, I am going to make it somewhat thicker. Okay, so this is the age that is going to be contracted. Now after the contraction, we will have a graph like this. E will not be there, but we will talk about ages later. Let us first look at vertices. So you pretty much understand what these vertices are. X and Y will vanish. So in their place, I have brought in a new vertex VE. Now the edges of the original graph that are unaffected by this contraction, let's just draw them first. And the edges that are affected by this contraction, let's first mark them in the original graph and then replace each one of them with a corresponding edge in the new graph. For example, what happens to this edge? One of its end is this one, the other is y, so in its place now we have v. So we just draw such an edge. Next, what about this edge? One of its ends this vertex, which is that same vertex you can see, and the other end was x previously. Now here the other end is v. So will you draw another edge? Clearly not, because we are not considering graphs to have multiple edges, I mean whose ends are the same but the edges are different. We are not considering multi graphs. Our edges, I mean our graphs don't have that kind of edges. Two vertices determine a single edge when there is an edge. So that means this one has been taken care of, this one has been taken care of. For this one you of course have this edge. Similarly, arguing, so this is gone. For this one you have this. What about this one? It will give you that same edge because x and y are becoming the same point. No, so these two edges will also merge if you think of it in that manner. This one of course will now correspond to this new edge. Okay, now it seems like we have simply not drawn the other edges, and we have in fact reduced the number of edges simply because our graphs do not have multiple lines between the same vertices, n vertices. But do we have that same facility when we write the set E prime using that notation and all the symbols? What will happen if there we don't carefully look at these things? I mean, for this edge you had one edge here. For this edge also you will write another edge. But because E prime after all is a union of two sets, and in the second set we are having edges which are the affected edges. So what will this correspond to? I mean, this edge will give you one edge here, this edge will actually give you another edge here, but those two edges will be the same thing, and in a set we don't usually repeat elements, and even if we repeat, it does not mean anything. It just means that same element is just an element in the set. So you don't even have to think about anything when you write E prime without thinking of anything and just simply applying the definition of E prime mechanically. Okay, so there is no problem with this. However, note one thing. Although the actual notion of this contraction does not involve just finite graphs, Potentially infinite graphs also are covered in this definition. But what happens when our original graph is finite? For example, in this particular example, our graph is finite. Can we say something about the order of the new graph? That is, how many vertices it has? Of course we can, because we are losing two vertices x and y, but we are gaining a new one. So that means that order of the new graph g by e is 1 less than the order of the original graph. However, what about the number of edges? What about the size of the new graph? The size of the new graph, at first sight, it seems like we are just losing the edge e, because that is being contracted, and the other edges, see, that is why that initial, you can call that discussion. I mean, before we wrote down the actual expressions for b prime and e prime, whatever we said or whatever the author said is just slightly vague, because it does not show you that you don't just lose e, but you effectively lose, at least in terms of the numbers, other edges also. For example, how many edges did G have, or does G have? 1, 2, okay, let us count like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I count it right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, 11 edges. So the size of G is 11, or this is 11. What about the size of G by E? 1, 2, 3, 4, 5, 6, 7, 8. It is slightly confusing. What about like this? 1, 2, 3, 4, 5, 6, 7, 8. Yes. So this is 8, which is not in fact 1 less than 11, it's in fact 3 less than 11. So in general we can say that this thing is less than or equal to this minus 1, because we are guaranteed to lose one edge e, the edge that is being contracted, but we may lose more because of this type of situations. Okay, so that is your contraction, but we haven't uttered the word contraction, I mean in writing, no? I think now the author will say. Oh, it hasn't been written at all. Anyway, this G by E is called a contraction of G by the edge E. And there is a more general notion. More generally, we have something like this. If X is another graph, G is already there, for which there exists a partition of the vertex set of G Another graph such that there exists a partition Vx where x belongs to the vertex set of this new graph. Partition of what? Partition of V with the following property. There exists a Vx Vyh in G if and only if xy belongs to the H set of E. Say this is something that is true. Then we say that G is an MX. We then call G and MX and write G equal to MX. Okay, now suddenly what is this? To understand this however is difficult to understand by drawing schematic diagram, general diagrams like that. We will take an actual example. And what does this new thing have to do with contractions? Oh, so this next graph, I hope I draw it correctly. Let us first see how many so that means first of all we have something like this. Okay, damn it. Not having labels for the vertices makes things very complicated. Complicated means there is a high chance of making mistakes. Okay. So here we have a rectangle. Then here also we have a rectangle. and so the situation is made even more complicated by the fact that there are other vertices in the graph which however have been drawn in a less prominent manner. Okay, let me just draw these vertices in a somewhat, let's make them slightly bigger than usual. And the less prominent vertices are small, and the less prominent edges are also there. Since it's difficult to draw less prominent edges, I will just use dashed lines. Okay, this one is there, then another one such is there. Anything else? Oh, this one is adjacent to these four vertices in a less prominent manner. I will explain why this different types of importance is given to some vertices and some edges. Anything else? Yeah, we do have these also. I think I have forgotten to write something here. I have missed one detail. V into of V. How do I? Okay, so you see, this is what happens when I don't follow the actual definition and start writing my own. I needed to mention that those sets Vx induce connected subgraphs of G. That I forgot. If X is another graph and that state is a partition of V into connected subsets such that for any two vertices X and Y in X. Oh, I did not mention this also explicitly. Anyway, there exists a Vx Vy H in G if and only if these two vertices form an edge in X, XY belongs to the edge set of X. If all these things happen, then we call G an MX. And write G equal to MX. Okay, now we can go back to this complicated diagram. Now what we are going to do is that we are going to now completely neglect the less prominent vertices and edges, that is which we drew like that. Okay, the vertices you can barely see and the edges have also been drawn as dashed lines. And draw the actual prominent part of the graph once again. I have been more or less able to retain the general shape so that you can at once see, because we don't have labels for the vertices, that it is in fact that graph that you see above. Oh, this edge is also there. Is that it? Now stay, okay. So this graph is not G, it is some graph Y. And this is our G. We still have some more things to show here, but this entire thing mentions another graph X. So in place of X, say we now have this graph. And this is our graph X. Okay, it's a completely different graph, some graph X. And in X, we have these two vertices X and Z, which are adjacent. Now what we are going to do, we are going to partition the set of vertices in G into, of course, disjoint sets whose union is the vertex set of G, and we keep these two vertices in one partition. You must understand that these extra things that now we are going to show, they are not parts of the graph, of course. So these three vertices belong to another set in the partition. These two belong to another set, and this one single vertex forms a single set. Now let us see what this entire thing is saying. More generally, if x is another graph, so this is your x and this is your g, but then what is this y? This the relationship between this y and g is just that g is a subgraph of y. So from y we have neglected some things, those are the less prominent vertices and edges, and we are now concentrating only on g. If x is another graph and this is a partition of v, v is what? V is the vertex set of g. That means the set of these vertices. We are partitioning this set into some disjoint subsets according to what? Each vertex in that new graph x corresponds to a set in this partition. So you can see that there are 4 vertices here, 2 of them are x and z. This vertex corresponds to this partition, this vertex corresponds to this partition, this one corresponds to this partition, and this vertex corresponds to this singleton partition set. Oh, I said correspond to partition, corresponds to partition set. Okay. And things are such that if you take 2 vertices in x, which are say x and z, these are adjacent in x. Here x and z are adjacent in x, there is an edge between linking them. Then the corresponding partition sets, so this is your v set and this is v x, are also linked. In what sense precisely? In the sense that there is a vx vy edge. A vx vy edge is an edge whose one end will be in vx and the other end will be in vy. In this case, of course, we have z in place of y. So because x and z are adjacent, so there should be an edge in g whose one end is in x and the other end, one end is in vx and the other end is in vz. That means we are talking about this edge. Okay, so the condition given here is matching for these 2 vertices. What about this vertex and this one? Let us name them also. Let us call this y and this one u. Then just like this is vx, this is vz, this becomes vy and this becomes vu. X and y are also adjacent, so there should be a vx vy edge. This is one such edge. Okay, so these edges are bridges between, links between these sets. Y and z are also adjacent. Now, so there should be vy vz edges. In fact, in this case we have 2 such, not just 2, 3 such edges. One of them is this, its one end is in vy, the other end is in vz. Another one such edge is this, another one is this. So we can just choose any one, at least one exists. That's what matters. And what about u? U is adjacent to x in x. So there should be a vx vu edge, which of course is this edge. And finally, u is adjacent to z. So there should be a vu vz edge, and this is one such edge. And another thing to note here is that this condition is if and only if. Not only should you have this kind of connecting edges, connecting partition sets, if their corresponding vertices are adjacent here in X, but if they are not adjacent, then there should not be such connecting edges in G. For example, U and Y are not adjacent. Is there a VU VY edge? No, because you see what the edges are that are coming out of VY. One of them is this, whose other end is not in VU. Another one is this. This end is not in VU. This one also has this end not in VU. And this one also has this end not in VU. Just like that, the edges coming out of VU, of course, do not have their ends lying in VY. So this situation is an example of this thing, all these conditions being true. If this entire thing is true, then we call this G and Mx and write like this. Now, what does this have to do with contraction? Do you see one thing? That if you think of these vertices in these partitions as the same thing, that is, you think of these two vertices as a single vertex. You think of these two vertices as a single vertex. This one, of course, we have only one vertex, and these three vertices as a single vertex. Then this graph becomes this graph. Just look at it. So that means, you can of course clearly see that, don't you? Let me just draw another figure, say here, say. To show exactly what I am talking about. Now, we have these partition sets. And these partition sets, clearly, because we made the association like that, correspond to these vertices. And there are connections between these partition sets in the sense that there is a Vy Vx edge in G, there is a Vx Vz edge in G. There is a Vy Vz edge in G. And of course this is Vy, this is Vz, and there are these links also. Oh, why am I writing this outside? I can conveniently write it inside now. V Z Vx, and this one of course is Vu. Okay, now you can think of this itself as a graph where you have four vertices which are sets. They can be, in fact, the vertices of a graph can be any type of objects, and we have them adjacent in such a manner that this graph looks exactly like this graph. The association between them being y corresponding to vy, z corresponding to vz, and obviously the other things. In the language of graph theory, this is isomorphic to this graph. Okay. Now, loosely speaking, what we are talking about here is that this graph can actually be turned into this graph, or the same thing can be turned into this graph by what? By contractions. What type of contractions? The edges that you have among the vertices in a single partition set, you are contracting those edges. But why? Because you want to make those vertices the same vertex, this vertex. It's like collapsing those points in a normal subgroup, collapsing the points in a single partition set. You treat this entire thing as one point, just like in the quotient group you treat a normal subgroup as one element, in fact the identity element. Here also you treat these two vertices as one object, which can, of course, technically speaking, what you will be doing here is that you will contract this edge. So you can see that in place of these already present edges, that they will now be replaced by a single edge. And what is that edge? That edge is this edge. Previously we had 2 points here in Vy. Now Vy is being treated as one object. So in place of these 2 edges, you have this single edge. When you contract these edges, that means you should get x. In other words, what we have described here is the result of several contractions done to the edges of a graph. That is, if you perform a number of contractions to a graph one by one, say you contract one edge, then in the resulting graph you contract another edge, then you will end up having something like this. Now what we are doing here is that we are not just simply doing this to G itself, but in fact you can see now, if you bring Y back into the picture, that there are other things besides these things in G. That is, in fact G is one part of a much bigger graph. Then what you are doing is you are doing contractions locally, so that whatever ultimately you get, that is going to be x. Isomorphically speaking, that is going to be x, but x then becomes a part of contracted y. The contraction that you have done in y is local only on G. If this happens, then we say that G is mx. Okay, so do you understand the relationship? I think now it's pretty clear. And in fact, this entire diagram, it has a name, or rather a description. Y contains G, which is equal to mx. So x is a minor of y. That means if you take one graph y and there you concentrate on a local part of y, that is a subgraph of y, you get some graph G. On G you perform several contractions, or maybe even one contraction, say. Then you end up having a smaller subpart of y than G. then that smaller subpart, that is not, you don't think of this smaller subpart again as a part of this original y. You just treat this smaller subpart as a graph in its own right, x. Then this x is called a minor of y. Okay, so that is the idea. And there is one more thing I did not discuss here. You have to also keep in mind that when you are doing this contraction, of course, when you are looking at this thing in terms of contraction, then you don't think of anything, you just simply contract edges, that's it. But because this is only an observation, see, I said that whatever we have here, whatever we are seeing here is likely related to contractions. It's just simply an observation, it has to be proved. That is, whatever we have described here, do we really get to this x from G through contractions? That's the thing next we are going to prove. But in this current form where we have nothing to do with contraction as yet, you have to keep one thing in mind, that whenever you are dividing the vertex set of G up into disjoint sets like this, when you are partitioning the vertex set G, the individual partition sets should give you connected subgraphs of G. So that's what we mean when we say partition of V into connected subsets. You look at the subgraph induced by each set, Vx, Vy, Vz. Vx, subgraph induced by Vx is this, K2. Here also you have K2. These are connected. Vu, of course, the subgraph induced by this is this single vertex, which is also connected in G. The subgraph induced by Vz is this path of length 2, which is also connected. We need this connectedness for proving that thing that I said just now, that in fact this thing what we have described here in fact is achievable through contractions, a number of contractions. Now these things have names. The sets Vx are called the branch sets of this Mx. G has now been identified as Mx, or that's what we are calling. So the sets Vx are called the branch sets of this Mx. Intuitively, that's whatever we discussed right now here. The author is now going to say that intuitively we obtain X from G by contracting every branch set into a single vertex and deleting any parallel edges or loops. Contracting every branch set means contracting the edges in that branch set, all the edges. Any parallel edges or loops that may appear. Parallel edges or loops means if you say you had this thing, you had two vertices here, now in its place you have this single vertex. Now if you are really treating these two links, this one and this one, these two links, these two edges as different, then you would be drawing parallel edges whose end vertices are the same, but they are multi edges, okay, and they are not allowed in our graphs. Just like that, you may end up having a loop. In fact, here itself you can observe that they are just simply generally saying, if you do not think of that contraction, if you are not paying mind to the edges actually, and if you are merging just vertices, then this edge itself that is being contracted, it will then turn into a loop having both its ends the same vertex. So such loops and parallel edges, if they appear, have to be removed, and then you get the graph X. In infinite graphs, also we have branch sets, but they are also allowed to be infinite. Are allowed to be in neat ink. Then the author mentions something which we will see in chapter 8, where we have infinite graphs. For example, the graph shown in figure 811. Figure 811 is an MX. with x and infinite star. We can understand just from the name infinite star what type of graph it will be. And there are infinitely many vertices adjacent to this one. I think that's how an infinite star looks like. But we will see all these things afterwards. Now, if now there is one special case. If Vx, which is one branch set Vx, which is U, is a subset of V, of course, where V is the vertex set of our original graph, is one of the branch sets above. And all the other branch sets are singleton sets, that is, each one of them consists of a single vertex, and every other branch set consists just of a single vertex. Consists of a single vertex. We also write G by U or G slash U for the graph X, and V suffix capital U, VU, for the vertex X belonging to X. We need not write anything else here because U is Vx. Okay, so X corresponds to U for the vertex X belonging to X, to which U contracts. Okay, let's just write, since we are anywhere writing to which U contracts. And treat the rest of X as an induced subgraph of G. The contraction of a single edge, yes, single edge U prime they are writing. defined earlier, yes, in G defined earlier can now be viewed as the special case where u is u comma u prime. So here what we are saying is that, okay, fine, so you have G and you have X. You have defined something which allows you to say that G is mx, or in other words, X is a minor of G, just like X is a minor of Y, but that graph of which G is a subgraph can be G also. Y can in fact be equal to G. So you can call X a minor of G if G is the graph where you are starting and you are not doing the contraction locally or anything. In fact, things are such that there is that relationship between G and X that in fact you can partition the vertex set of the entirety of G, maintaining those conditions. Okay, then G itself is mx. Okay, now what happens is that, say you now have a situation like this, that the vertices in G have been partitioned like this. Exactly one branch set U, which is Vx for some vertex x here, likely has more than one vertex. It may not have more than one vertex, but the other branch sets, whatever else, all of them are singleton. Each one of them has exactly one vertex. Then you can denote this x by the notation G by U. Do you see why we were discussing back then about this notation and why it should be like this? It's because now what you are doing is that you are going to collapse U. You are going to make U collapse, and that will become a single vertex. The other partition sets or the other branch sets will also suffer collapse, but those collapses are trivial. This one is likely non-trivial. This one will be trivial if there is precisely one vertex here also. Otherwise, it will be non-trivial. So, essentially what is happening is that you are making U collapse, and that is giving you a new vertex x, and that new vertex, well, not x, but that new vertex in fact we are denoting by Vu. So everything is caused by U. So that is why here the reducing element or the reducing agent, if you want to call it that, is U. So we are using a notation like this, G by U. And for the vertex U, to which U contracts and treat the rest of X, whatever else you have in X, they are practically already also there in an almost unchanged form in G. So view the rest of X as induced subgraph of G, because they are directly coming from G without essentially any change. And the special case where this U in fact has only two vertices and a single edge between them, U and U prime, matches with our original notion of contraction. So that is why this new thing that we have defined, this mx, getting x from G or identifying G as mx is in fact a much more general concept, and contraction is just one special case of that, and that is that case where U is this, two adjacent vertices in G. And now let me just simply state the next result, which may have become obvious by now. That thing that we were claiming, that in fact this X is achievable by a number of contractions from G. The precise statement is this result, which is proposition 171. G is an mx where of course G is a graph, X is also a graph. G is an mx if and only if X can be obtained from G by a series of H contractions. More formally, i.e., if and only if there exist graphs and edges EI belonging to GI such that the first graph G0 is just G itself, the last graph Gn is isomorphic to X and Gi plus 1. The I plus 1th graph is the ith graph where you have contracted the edge EI for all I less than n. So that means G is an mx in that sense that we have discussed right now, that is those partition and all those things, if and only if there is a series of H contractions like this that will get you to X starting from G. This we will prove, and we will see other things in the next graph theory video. So today is Tuesday, so that means coming Friday let us again do field theory. So with that I end this video. I in fact wanted to prove it today, but I did not realize it will be so long. It takes time for these things to properly sit in our brains. Anyway, so that's just it for tonight. If you want to make some comment, you are welcome, and you can also send me mail. The link will be there in the description, my mail ID. So that's just it. See you on Friday with field theory. Until then, have fun with mathematics. This is me, Lucifer, from a mathematical room. Have a nice night.